to talk about just one section. One section is called section 3.7, rational functions. Okay. So let me introduce this topic for you by telling you about this example that is in our free OER textbook, OpenStax. It says the following. Suppose we know that the cost of making a product is depending on the number of items X produced. This is given by the equation C of X, 15,000 times X minus 0.1 times X squared plus 1,000. If we want to know the average cost for producing X items, we would divide the cost, the total cost, right, by the number of items X, right? Yeah, so basically, we are used to working with these functions, right? Polynomial functions, right? But what this example is suggesting is this. What if we are interested in not in the total cost, but the average cost per unit produced? Well, then inevitably, we have to end up with this idea, the average cost function, which yields the average cost per item X, items for X items produced, is going to be this, right? Total cost divided by the number of items produced. This will give you the average cost, right? So you can see out of a polynomial function, we ended up with this new function that looks like a fraction, right? Like a rational expression. So mathematicians notice that this happens a lot, that when we do modeling, we may have to take two polynomial functions and divide them, so we will end up with this type of functions, right? They studied this deeply and they call them rational functions, because they resemble rational expressions, fractions, right? Fractions. A rational function is defined as the quotient of polynomials. In its general form is f of x equal n of x, a polynomial on the numerator, and divided by d of x, another polynomial in general on the denominator, where n of x and d of x are polynomials, and never let d of x be equal to the polynomial 0, right? D of x cannot be the 0 constant polynomial, because if it is, we will be in trouble because division by 0 is undefined, right? It's undefined. All right. So now, examples of these rational functions. This is not the only way to create a fraction out of two polynomials, right? Look, this is another, for example, f of x equal to x plus 1, linear polynomial, degree 1, divided by this other linear polynomial, 3x minus 4. This is called a rational function. Now, the polynomials may not have the same degree. So you can form another rational function by taking a linear polynomial, degree 1, divided by a quadratic polynomial, here degree 2, x squared minus 4x plus 7, right? And then you got yourself another rational function. Here is another example, 6x on the numerator divided by x squared plus 1. These are all rational functions, right? We're going to study them in details now. Okay, now, first thing that you should learn about rational functions is this. Very often, 99.9% of the time, they will come not all in one piece. They will not be connected. They will have gaps, jumps, holes. In order for you to understand that, let me go over this example. And this is related to the fact that we got to be careful with the denominator, right? If the denominator is 0, there's no way to evaluate this function, right? The function will be undefined. So in order to emphasize that limitation, let me give you this example, right? We're going to study this in details, and then from there we will generalize this idea of these graphs of rational functions coming in pieces. You will see. Example 1, given this function f of x equal 1 over x. This is called the reciprocal function, right? We studied this in our, it's one of our, I think, parent functions, reciprocal function 1 over x. It says it states its domain and a sketch its graph, okay? First, let's state the domain. the domain is clearly going to be all real numbers except 0, because 0 is the only number that's going to give me trouble here, right? 0 into 1 undefined, right? So domain, all real numbers except 0. Now let's go into the graph of this function. In order to graph this function, one thing I can do is this. I can allow myself to have some input values, right? And then evaluate them, look at the output values, and then pair them up and come up with a graph, right? If we do that, look, if the function, recall, is f of x equal 1 over x, right? F of x equal 1 over x. So notice if x is 1, 1 over 1 is just 1. So 1 should be paired up with 1, right? So here I have a point. 1 should be paired up with 1. If x is 2, 1 over 2 is 1/2, but 1/2 is 0.5, right? So 2 should be paired up with 1/2 here, right? Another point, right? And if you go to the extreme of taking a very, very small value for your x, meaning a value very, very close to 0, I have chosen 0.001. I want you to do in your calculator this, 1 over that number. What is that? 1 over that number, 1 over 0.001. Notice it's a very big number, right? Very big number is 1,000, right? So this is going to tell us something about the trend of this. So 1,000, right here, 1,000. So this very, very small number, very close to 0, will be mapped with 1,000, somewhere up there, right? Somewhere up there. But the idea is that if you connect these two dots together with that 1,000 up here, you're going to get this curve, right? You're going to get this curve. Okay. Now, similarly, if you go to the left, right? If you use negative input values now, look, notice, if you take -1 divided by or into 1 is just -1, right? So -1 should be paired up with itself, -1 here, right? Then -2, 1 over -2 is -1/2 here, right? Here, -1 here, right? And if you go really very, very close to 0 from the left, -0.01, if you use your calculator, notice you're going to get now a very, very large, between quotations, negative number, -1,000 now, right? Very negative, this number, right? -1,000, and that's what it goes here. So if you are very close to 0 from the left, the output value will be -1,000, somewhere down here. I cannot even put it there, right? But the idea is that if you connect these dots together with the one that has as an output value -1,000, you will get this other piece, right? This other curve. So notice the graph of this comes broken in two pieces, one here, right? Now, guys, if you want to remember this graph, you want to visualize it, play around with it, use our Desmos graphing tool, right? Graph y equal 1 over x. What do you get? You get what I just got here, right? This is sort of presented in this way, right? Notice that this curve gets closer and closer to this y-axis, never touching it, right? Very important detail. And same as over here, look, the curve gets closer and closer to x-axis, never touching x-axis, right? Very good. So this is the graph of y of x equal 1 over x. Now, mathematicians, notice that this line that you see here, right, this vertical line is important. Why is it important, Professor? Well, notice this line, which in the graph is this one, right? This vertical line y-axis, kind of separates the two pieces, right? And also notice the curve gets closer and closer to it if you approach to 0 from the right. And the curve gets closer and closer to this vertical line if you approach 0 from the left also, right? From the left. Okay, these type of lines, the ones showing this behavior, are called asymptotes. Asymptote. So mathematicians call this vertical asymptote. And the equation of this vertical asymptote is x equal 0, right? X equals 0 is the equation of this vertical line. So this, guys, is going to be our vertical asymptote. Now, notice that the following is happen for this vertical asymptote to appear there, right? When x approaches zero from the right, right? And for that, mathematicians, they use this notation. They're going to put a plus sign on top of the 0. This means from the right. Let me write from the right. From the right. And try to catch these guys, because in calculus, you're going to use this when you talk about limits. Okay, when x approaches 0 from the right, what is happening with y? Y is blowing up. It's going up here, right? It's going up here. Then f of x approaches infinity. And this is the first thing you have to catch, because I'm gonna ask you questions about it soon. Right, when x approaches 0 from the right, the positive sign on the top, then f of x, the output value, goes up to infinity, right? Positive infinity, remember, lives here. Okay, now, if we go over here, from the left, now this was from the right, well, it's right here from the right, now from the left. When x approaches 0, now from the left, this negative sign that you're going to see on top of the 0, from the left, that's what it means, right? From the left. When x approaches 0 from the left, then f of x, the output values, right? The corresponding output values, where is it going? Look, if you approach 0 here from the left, look at the output values. They're decreasing without bound, right? They're going to negative infinity, right? Negative infinity. This is the arrow notation. Remember that I introduced yesterday to you. You're going to use this in calculus. Try to understand this. There will be some exercises coming up soon. All right, so this is for the vertical asymptote, right? But now you see this other line also here in red. This also kind of shows something similar to the blue line. The curve gets closer and closer to it, never touching it, right? In this direction and also in this direction, right? This is what mathematicians call a horizontal asymptote. So I'm going to write here horizontal asymptote. Okay, this is this guy. This in red, right? This line. And this horizontal asymptote has an equation, right? An equation. Remember the equations for horizontal asymptotes? We're going to write it here below. Has an equation. Professor, what's the equation? Y equals 0, right? Because all the y second coordinates are equal to 0 for those points here, right? So the equation is y equals 0. It's a horizontal asymptote, right? Now, using the arrow notation, when x approaches plus infinity, if x is going in this direction, where is the y output value going? Well, if x is going in this direction, notice, right? If you're going this way, the output values are decreasing and decreasing, headed to 0, but never actually being 0, right? Getting closer and closer to 0. So that you can express by saying that then f of x, the output value, approaches 0, right? When x approaches plus infinity, the output values, they approach 0. And over here, you can see the following. When x approaches, this arrow must be read as approaches, right? Approaches what? Negative infinity now, negative infinity, right? If you're going in this direction with the x values, right? Where is the f of x approaching? Then f of x approaches, look, if you're going in this direction, your output values are decreasing, right? Decreasing towards 0. They're never going to be 0, but they get closer and closer to 0, right? So it's 0. Follow, guys? All this stuff, guys, in calculus, you will get to see it in deeper, right? When you talk about limits, but try to build up the idea there. All right, for you to kind of get better at this, let me give you quickly a couple of examples, okay? Try to do this using that notation that we just saw, right? These two guys. For example, this. Can you try this? Mm-hmm. It says use the graph of the rational function shown to complete the statement. Basically, they are saying, right, as x approaches, remember arrow approaches 2, there is a positive sign, hint, this means from the right, right? From the right. As x approaches 2 from the right, what is happening? What is happening with f of x? Can you figure this out? Right? Is it going to positive infinity, negative infinity, 0, 1, negative 1? Try to figure this out, guys. Mm-hmm. 2 from the right, right? From the right. Hint, notice you are approached this way, right? This way, from the right to 2. The number 2 is here, so try to approach from the right. This is important, this right from the right, this way, right? Try to see where these arrows are going. Yeah, very good. I see already students posting answers. Very good, very good. Savannah. Excellent, excellent. Very good, good thinking, right? Yeah. And this guy is going to help you tremendously when they talk to you about limits in calculus later on, right? Yeah, very good. Excellent, excellent. Look, they say approach 2. This is the number 2. We can put it in highlighted. This is the number 2. But from the right. So you got to go this way, right? Notice where the output values are going. They are going to this guy, positive infinity, right? They're blowing up. They're going without bound, right? Positive infinity. So this is this. So positive infinity is just infinity. But in this case, they put a positive, doesn't matter, doesn't hurt, right? So this is it. Excellent. Try the next, and then we will move on, okay? Try this now. Using the arrow notation. Try to get used to it. Do this now. Right? So a little bit tricky. It says now, what happened as x approaches -2 and with a negative sign on the top? This guy, remember, from the left, You're approaching the number -2, but from the left. So be careful there, okay? On the left. Yeah, the number -2 is here, right? And you are approaching from the left. I see students posting answers. Savannah, Savannah, you made my day. Excellent, excellent. Good thinking. Good, excellent. Good. So this is the number -2, but now we are approaching to -2 from the left. So from here, right? So what you gotta do? Hint, right? Try to approach this way along the curve, right? Travel along the curve and try to approach the input value -2 from the left. Check or figure out where the output values are going. Clearly, the output values are going down here, right? Decreasing without bound, headed to negative infinity, right? So this is the one you have to pick. You follow, guys? Yeah, not that difficult. No computations here. You just have to trace the graph of the function, right? Accordingly, the signs are important, right? On top of it, from the left and the right. Excellent. So now let's go back to the formal definition of vertical asymptote and horizontal asymptote, right? So we know informally what these asymptotes are, right? Are lines such that the curve approaches to them, never touching them, right? For big values of x, either on the right or on the left, big absolute values of x. So mathematicians came up with this formal definition for the vertical asymptote. They say the line x = a is a vertical asymptote of the graph of f when the following happens. When f of x approaches infinity or f of x approaches negative infinity as x approaches a, right? If you see that behavior, right? If you see that your curve is kind of approaching a vertical line, right? From the left or from the right, right? Doesn't matter really. Mathematicians say this you should call a vertical asymptote, right? A vertical asymptote. A vertical line, the graph approaching to it, right? From the left or from the right, vertical asymptote. And similarly, they have defined the line y equal b as a horizontal asymptote of the graph of f when the output values now are headed to some specific number. In our example, that number was 0, right? 0. But it could be any number, right? If you notice that the output values are going to some real number as x approaches positive infinity or as x approaches negative infinity, then you got yourself a horizontal asymptote. Okay, great. So now I'm going to tell you how we can computationally find those vertical asymptotes first, and then I will tell you how to find the horizontal asymptotes. Let's start with this vertical asymptotes first. Method to find vertical asymptotes of these rational functions, right? 2 steps. First step, very important, simplify. Simplify your rational function, the way you learn in previous courses, right? For you to remember how to simplify, use factorization if possible. Factorization helps to simplify. Second step, set denominator equal to 0. Remember, the problem with these rational functions is the denominator, right? At all costs, we have to avoid this denominator being equal to 0, right? So this is the justification of the second step, right? Set denominator equal to 0. From there, you will be able to see your vertical asymptote. Let me show you how. Let me apply this nice method to this example 1. Example 1 says, right? Given this rational function f of x equal 3 over x minus 4, find the vertical asymptote VA, shorthand for vertical asymptote, okay? And within parentheses there, writing an S, because it could be that there is just one vertical asymptote, but perhaps there will be 2 vertical asymptotes. We will see, right? Maybe 3, right? But we will go up to 2 perhaps in this course. All right, so let's do it together, right? So let's follow the method. First, it says simplify. But notice that this is simplify first, right? Simplify. But you notice that this guy, it's already simplified, right? It's already simplified, right? F of x equal 3 over 4 subtracted from x is already simplified. We're starting with something very simple, right? Simplify. Checks, yeah. First step checks. Second step says set denominator equal to 0. So once you have simplified your rational function, you take the denominator and set this equal to 0. Set x minus 4 equal to 0. We don't want this to be 0, right? Let's find out by solving this equation for which values of x this could give us trouble, right? This could be equal to 0, the denominator. Turns out that happens at x equal 4, right? So then conclusion, the vertical asymptote is going to be given by this equation, x equal 4. This is the vertical asymptote, okay? And then we are done. So that's it, right? X equal 4, vertical asymptote. Now, Professor, can I visualize this? Can I really see that this is the vertical asymptote for this function? Yes, guys. Use your graphing tool. Let's see, right? If indeed that is the vertical asymptote. Okay, I'm gonna graph f of x equal 3 over x minus 4. Aha, you can see it there, right, guys? See this vertical line separating the graph to parts, right? This is the vertical asymptote, right? And notice how it happens precisely at x equal 4, right? Look, 1, 2, 3, 4, right there. There is this x equal 4 vertical asymptote, right? If you want to see it there together with the graph, you can choose x equal 4, and it's there, right? This blue vertical line is the vertical line, right? You see it? Very good. Always confirm your result, guys. If you get something you're not sure, you don't visualize it in your mind, use your graphing tool. We have this graphing calculator, right? Makes sense out of things. All right, great. That's for the vertical asymptote. The method works. So now let's go over a more challenging example. This, guys, is a little bit tricky. I hope you will remember when you go over your homework, when you take your examination. Suppose they give you this other rational function g of x, x minus 5 over x squared minus 25. Let's follow that two steps. Step 1 says simplify, right? This is a very important step, simplify. So in order to simplify, my rational function is this x minus 5 over x squared minus 25, right? In order to simplify this, what I'm going to do is I'm going to factor. I'm going to factor the denominator. How can I factor this guy, the denominator? Well, this is the same as x squared minus 5 squared, right? And there, I can use difference of squares and conclude that this is x minus 5 times x plus 5, right? Follow, guys? X minus 5 on the top. Notice that this guy and this guy are the same, right? So we can cancel them, right? We can cancel them. So notice that this time, the simplification is telling us that this function that look complicated here is just really this other function in disguise. Notice that when you divide this into this, that's 1. You have to put the 1 on the top. And here x plus 5, right? This is telling us that this function is in reality just this guy, right? Yeah, in disguise. So this means that for step 2, I have to work with this function, right? Not with this, right? I have to set for step 2, denominator equals 0. Denominator equals 0, right? But what denominator? This or this? Well, it has to be this, the one that appears on the simplified version, right? So that's why it's very important to simplify, guys, because otherwise it's gonna mislead you. It's gonna give you two asymptotes when in reality there is just one. This cancels. X equal minus 5 should be our vertical asymptote, right? Vertical asymptote, let's write it straight, is x equal negative 5. Just one vertical asymptote, right? Only, right here, only one vertical asymptote, which is this guy, right? Now, you want to confirm this, right? You want to check this out. So is in reality this the only asymptote? Only one vertical asymptote. It is this, right? Yeah, you can always confirm, guys. Check this in the grapher, in the graphing scientific calculator. G of x equal x minus 5 over x squared minus 25, right? You can see there is just one vertical asymptote, right? And this located precisely at x equal minus 5, as you can see there, right? There are no two, right? If you set this equal to 0, you're going to get two vertical asymptotes. There's just one, and it's located at x equal minus 5, right there, right? Very good, very good. Okay, guys. So now that you have seen these two scenarios, right? Let's go over one more example, and then I will give you something to work on. Can you, let's see example 3, right? And then we'll go to a worksheet. Another example here. Is it possible for a rational function to show two asymptotes? Answer yes. Here is the example. Suppose they ask you to find the vertical asymptotes of this rational function. Step 1, simplify, right? Simplify. For that, you are going to recall how to factor, right? Remember this type of expressions. Factor, right? Factor. Remember to factor this quadratic trinomials, you look for two numbers whose multiplication is -8, whose sum is 2. After some trial and error, you will end up with 4 and 2. The sum you want to be positive, so this has to be negative, this has to be positive, right? So that's the factorization, x minus 7 here. But now notice that there is nothing to cancel there, right? There is nothing to cancel this time, right? Could be nothing to cancel. This is 7, this is 2, this is 4, nothing to cancel, right? So in simplified form, h of x is just this, right? It's just this. We're not able to cancel anything there, right? It's this. Very good. Now go over the second step. The second step is set denominator equal to 0, right? And this is something that you have to recall, guys, for your homework, right? They give you some challenging rational functions there, but it's all about simplifying and then setting the denominator, right? Denominator equal to 0. Sometimes when I'm going over this, students say, Professor, the denominator equals 0. What about the numerator? The denominator is the one because numerator could be 0, right? That's not a problem. The problem is having denominator equal to 0. So you set this equal to 0, and from there, the rest is just this, right? Set each factor containing the variable equal to 0. From there, you will get that x is equal to 2. It's going to be the first vertical asymptote. But together with this, there is another one here, right? X equal -4. Second vertical asymptote, right? Two vertical asymptotes, Professor. Yes, guys, two vertical asymptotes. You want to see it? Always not a bad idea to check this out in our Desmos graph, right? H of x equal x minus 7. Highlight this slash. You can write it in factor form in its original form. Does not matter, really, does not matter. So, but I want you to see these two asymptotes there. You see the two asymptotes, guys? Look, one asymptote, one vertical asymptote is here precisely at x equal 2. This is this one, right? This vertical asymptote. You can put it here. X equal 2. It's there, right? That's the vertical asymptote. Then there is another vertical asymptote here that corresponds to x equal -4. Look, -1, -2, -3, -4. You want to see it, you can write here type x equal -4. There it is, right? See, two vertical asymptotes. This rational function comes in 1, 2, 3 pieces, right? 3 pieces. This is very common in rational functions. They come in pieces. All right, great. So play around with this graph, guys. Confirm your knowledge always. Great. Now, let me ask you to do some work on your own, right? Some work on your own before we go to the break. So let's see if you can do something here. Can you try this too? Let's start with number 3. Can you do this? Find the vertical asymptote, right? Or vertical asymptotes. I see the students posting answers. This is number 3. 2-0. Excellent, Savannah. Very good. Very good, guys. Yeah, so first step, simplify, right? But this is already simplified, right? So it's already simplified. So we go over step 2, right? Simplify. It's already simplified. Go over step 2, set denominator equal to 0, right? So this guy equal to 0. Solving this will tell you where the vertical asymptote is. So it's just x equal 1, the vertical asymptote, right? Very good. So this guy. Can you try number 4? It's a little bit tricky, I should warn you, but do it. Do number 4. Remember 2 steps, simplify. And then after you simplify, you set the denominator equal to 0. I see students are posting readily answers. Lucero, very good, very good. Excellent, excellent. Very good, good thinking there. Yeah, first simplify, right? First simplify. Don't forget this first step, simplify. If you simplify this guy, x plus 4 over x squared minus 16, this x squared minus 16 can be factored, right? Can be factored. You learned this guys in previous courses. It's 2 squared, 16, right? So these factors. So x minus 4 times x plus 4. It's called difference of squares, right? Maybe I should write here, recall a squared minus b squared is equal to a minus b, or factors as a minus b times a plus b. Better said. Yeah, great. Yeah, so, but now notice that out of luck, this guy is exactly this guy, right? So we can cancel these two. Yeah, this and this, sorry. We can cancel those two, right? Yeah, we can cancel those two. And this is telling us, guys, that this rational function, it's in reality simpler than it looked like, right? It's just this. It's just this. So we're going to work with this, right? Step 2 is set denominator equal to 0. But what denominator, Professor? This denominator? No, this one, the one that is the one from the simplified version, right? Be careful there, guys. Yeah. Try to remember this for your examination, for the homework, right? Yeah, otherwise misleading. X equal 4. This is the vertical asymptote, right? Vertical asymptote, x equal 4. Not this, right? This is not the one. This is just one vertical asymptote. And then you can always check and confirm. You will see that when you graph it, you will see just one. Very good. There is another one here. Can you try this? And then we will take a break. So try this one. And try to remember these guys when you do your homework, okay? Yeah, great, great, great. Try this one, number 5. Tricky, tricky. Yeah, I can see students are really posting answers in the chat room, which is good. Lucero. Very good, very good. Excellent, excellent, excellent. Good job there. Great. Follow the steps, right? The 2 steps. First step 1 says simplify, simplify. Well, if you simplify this guy, well, you have to factor the denominator, right? Denominator. So x squared minus 13x plus 36 must be factored, right? Factor is factor. But how you factor this quadratic trinomial? Well, remember, you do this sort of FOIL in reverse, right? You think of 2 numbers here whose multiplication is 36, whose sum is negative 13. After some trial and error, guys, you will end up with this 9 and 4, right? You want the sum to be negative 13, so this has to be negative. This has to be negative, so the sum negative 13. Product is still positive 36, right? Great. Now set your denominator, the denominator, which is this, because nothing gets canceled, right? This is 16, this is 4, this is 9, nothing is canceled. So it's just this. So this guy equal to 0, and from there you will get your asymptotes. You will get 2 vertical asymptotes here. Let's see. So x minus 4 equals 0, x minus 9 equals 0. Here, adding 4 to both sides, x equal 4, first vertical asymptote, right? But there is another one here, adding 9 to both sides, x equal 9, right? So we have x equal 4 vertical asymptote, x equal 9 vertical asymptote. So this guy, right? Follow guys? Excellent. All right, so let's erase this part and let's continue here. Let's talk about horizontal asymptotes now, right? We know how to find vertical asymptotes. I gave you a method, right? Two-step method. Now let's talk about how to find horizontal asymptotes. So this comes next. Here. Method to find horizontal asymptotes. All right. So for this, mathematicians have developed this method, which deals with three possible scenarios for a rational function. If you are given a rational function, which is going to look like a fraction made of two polynomial functions, right? One on the numerator, one on the denominator. In general, these two polynomial functions will look like this, right? An times x raised to n, and then gradually the exponent goes down to 1, a1 times x plus a0. These guys, when you look at these things, don't get freaked out. These are just general representations of a polynomial function, right? Of any degree, in this case, degree n. Now, that will be divided by another polynomial, right? Not necessarily the same as this, right? So for that, mathematicians use a different letter here for the leading coefficient b, bm times x to the m, right? Where m not necessarily equal to n, right? Then gradually you go down to b1x, b0, the constant term. But notice that this m could be any number different than n, right? So it's the degree of the polynomial on the denominator, right? Now, first, mathematicians say simplify, right? Simplify. So I'm just writing here in simplified form, right? Assuming that you have already simplified this, right? What to do to figure out the horizontal asymptotes of this rational function? Well, three scenarios, right? Out of comparing the degrees of n of x, the polynomial on the numerator, and d of x, the polynomial on the denominator, right? Out of comparing these two numbers, n and m, three possible scenarios. If n is less than m, then the horizontal asymptote is going to be y equals 0, y equals 0. Okay, let's explain this, right? So they're saying compare this guy with this guy. If the dominant is on the bottom, right? If n less than m, this is the dominant, right? Then y equals 0 should be the equation of the horizontal asymptote. Now, in order for us to remember this, let's try to identify this type of functions, the ones that have the dominant exponent on the bottom. Let's call them bottom heavy, okay? Bottom heavy. So this guy is a bottom heavy rational function. Why? Because the bottom is dominating, right? In the sense of the degree. So this one, let's call it bottom heavy. So conclusion, guys, for bottom heavy rational functions, they come with a horizontal asymptote y equals 0, right? Bottom heavy. Now, but what about this other scenario? Suppose that when you compare n and m, you get the same values. Suppose n is equal to m, right? What to do? Well, mathematicians have figured out that in that case, if n is equal to m, then in that case, the horizontal asymptote is given by this equation, y equal an, right? Look at this guy, the first number appears here, leading coefficient, divided by this guy, the first number that appears on the denominator, right? Going from left to right. And this quotient will determine the equation of your horizontal asymptote, y equal an over bn. And this, in order to remember this type of rational functions, we're going to call them equally heavy, okay? Equally heavy. Equally heavy, yeah, because same degree, right? Last scenario, what if this is the dominant, n bigger than m, n bigger than m? So what if this guy bigger than this guy? well, mathematicians have discovered that then no horizontal asymptote. There is no horizontal asymptote, okay? And in order to identify this situation, we're gonna call this type of rational functions top heavy, top heavy, top heavy. So why you call them top heavy? Because this guy is the dominant, right? Top heavy, the dominant, n bigger than m, right? So for top heavy rational functions, no horizontal asymptote, right? These are the three conclusions. Right, let me give examples of each scenario. First scenario says f of x equal to x plus 3 divided by 5x squared plus 2x minus 4. Find the horizontal asymptote, between parentheses asymptotes, right, in case there is more than one. All right, let's follow this method, right? The method says compare the degrees, right? The degrees. So the degree of the polynomial on the top is just this invisible one, right? Degree 1. The degree of the one on the bottom is this 2, right? Degree 2. So anyone could tell me, is this a top heavy, bottom heavy, or equally heavy rational function? Anybody could write in the chat, top heavy, bottom heavy? What kind of rational function I am looking at? Yeah, I see here. Yeah, Jing, excellent, right? Yeah, it has to be bottom heavy, right? Bottom heavy because the dominant exponent is on the bottom, right? Bottom heavy. So this tells us that then, right here, things 2 greater than 1, right? Then the conclusion is horizontal asymptote is y equals 0, right? This is right for bottom heavy, right? Bottom heavy, y equals 0, horizontal asymptote, right? You got it, guys? Very simple. Now, number 2, given this function, find the horizontal asymptote. So again, guys, question for you: is this bottom heavy, equally heavy, top heavy? What kind of rational functions we are looking at there? Hint, look at the, yeah, very good, very good. There are solutions. Very good, Jin, right? Yeah, equally heavy because the degree here is the same, degree 1, right? Degree 1, degree 1. So equally heavy. Degree 1, degree 1. And what does the rule say for equally heavy functions? Degree 1, degree 1. Equally heavy then it says that the horizontal asymptote, shorthand for horizontal asymptote is h dot a dot, will be given by this equation, y equal the quotient of these two guys, right? These two guys, this over this. Take this part, 3 over 7, right? 3 over 7. Very good. All right, excellent. All right, now this third scenario, given h of x equal 5x cubed minus 2x plus 3 divided by 2x squared minus x plus 2, find the horizontal asymptotes. If not, if they don't exist, say they do not exist, right? Or no horizontal asymptote. But this one clearly now, what is this? Top heavy, bottom heavy, equally heavy. Very good, Jin. This time, this exponent 3, the degree here 3, is the dominant, right? So we are dealing with, mathematicians call it top heavy rational function, right? Top heavy. The dominant is on the top, right? But then the conclusion is no horizontal asymptote. You will see a choice for this, okay? No horizontal asymptote. Very good, guys. Very good. Excellent. Now, let me ask you to practice. Let me give you some practice here, and then we will move on to graphing these rational functions, and probably we'll do some stuff with slant asymptotes, right? Find the horizontal asymptote. Now, let me choose some exercises for you to work on. start with this guy. Number 6. Try this. What is the horizontal asymptote, right? Figure it out. I see quickly students are participating. Yeah, the hint, yeah, I think Jingjing, we have to adjust there. Look, notice this is 1, right? 1, degree 1. This degree 2, right? Yeah, so try to find out if it is bottom heavy, top heavy, or equally heavy. Now, Savannah, yeah, very good. Now, Jingjing, yeah, it's fixed, very good, excellent, excellent, right? Notice degree 1 on the top, degree 2 on the bottom. Tells me that this is bottom heavy, bottom heavy, bottom heavy. So therefore, for bottom heavy rational functions, the rule says that the horizontal asymptote is this, right? Y equals 0. This is the equation of the horizontal asymptote, right? Excellent. Try this now. Number 7. Do this now, guys. What should be the horizontal asymptote, the equation of the horizontal asymptote there? Yeah, Savannah, very good. Lucero, very good. Excellent, right? Notice that this has exponent 2, equally heavy, right? Equally heavy. For equally heavy rational functions, horizontal asymptote is just this. Y equal, you take the quotient of these two guys, right? So it will be 5/3. Yeah, very good, very good. So this guy, right? Excellent, excellent. Next, let's see. What about 9? We'll move on, right? The others you can do it at home. 9. Maybe I can make it a little bit bigger. Yeah. Let's see. Jing. Yeah, you made my day. Very good. Savannah also. Very good. Excellent. Excellent, guys. Very good job. Yeah, quickly, you realize that since the exponent here is 3, degree 3, exponent here degree 2, we are dealing with a top heavy rational function, right? For top heavy conclusion, then no horizontal asymptote, and it will be clearly stated that you're gonna go for this, no horizontal asymptote, right? Very good, very good. The others, guys, do them at home, figure them out, okay? They're easy, doable. Now, let me talk about graphing these rational functions in general, okay? Graphing them in general, and in the end, we will see slant asymptotes, oblique asymptotes. So let's go back to the notes, and let's talk about how we can set up a method to graph these rational functions in general, right? So, this is it. Yeah, we did this, sketching the graph of a rational function. This word sketching, guys, very important. It means that when you graph this rational function, since we are doing pre-calculus, they don't expect your graph to be perfect, right? They expect you to show the main features of the graph, right? Such as asymptotes, right, and stuff. But then somehow you should come up with a nice sketching, right? Sketching of the graph. Later on in calculus, they'll give you more sophisticated tools such as derivatives and stuff. Then you will be able to do this in details, right? But for now, method, follow these 6 steps, okay? Step 1 to graph a rational function is factor and simplify. Remember, simplifying is very important, right? Factor and simplify, first step. Step 2, find the y-intercept. Let x be 0 and solve for y. Step 3, find the x-intercept or intercepts. Let y be 0 and solve for x. Step 4, find vertical asymptotes. I gave you a method to find vertical asymptotes, right? Follow that method, find your vertical asymptotes. Step 5, find horizontal asymptotes. I gave you also a method to find horizontal asymptotes, right? Follow that method, get these guys. Step 6, use test points and smooth curves to complete the graph, right? Remember, when you graph these rational functions, they come in pieces, right? But those pieces somehow, they are smooth pieces, right? We're gonna assume that. So connect the dots with the smooth pieces and then figure it out, okay? Yeah, let me explain to you how you do this step by step, okay? I'm going to use this example, which is exercise 1 in the worksheet that is coming up in this worksheet, okay? So we're gonna do this here step by step. This problem we're gonna do, right? I'm gonna show you which is the graph. All right, so start with the step 1, which says factor, right? Factor and simplify, right? Simplify, factor and simplify. So let's start with that. So step 1 says factor and simplify. So step 1, start with this 3x on the numerator, on the denominator x squared minus 4, right? But this is x squared minus 4 can be factored. How, Professor, you're gonna factor this? Well, recall, right, guys, that this 4 is just a perfect square number, right? It's 2 squared, right? And as such, 2 squared, right? X squared minus 2 squared factors as x minus 2 times x plus 2, right? Using what mathematicians call factoring a difference of 2 squares. So we factor and then we simplify, right? Notice that nothing is simplified. The function stays the same, right? Because this cannot be canceled with this. So this is just showing us the structure of this rational function, right? Great. Simplify, right? Simplify. Good. Step 2. Let's see what step 2 says. Step 2 says you're going to find the y-intercept, y-intercept. What do you do to find your y-intercept? Well, set the other variable, in this case, x equal to 0. Set x equal to 0 and solve for y, right? So y, f of x, you gotta figure out what is this y when x is 0, right? Either on the original form or the factor form, doesn't matter. Notice this is 0. This is -4. -4 into 0 is just 0, right? 0. So we get that our y-intercept then is going to be what? Y-intercept is going to be 0, comma 0, right? 0, 0, 0, is our y-intercept. We found the y-intercept. Step 3 says find the x-intercept now, the x-intercept. Universal method to find the x-intercept is set the other variable, in this case now, y equal to 0, right? Set y now equal to 0 and solve for x, right? And solve for x, that's the idea, right? Right here is in case you want to remember this. Set y equals 0 and solve for x. That is how you universally find your x-intercept, right? So here the y now 0, and then you are supposed to solve for x. You get this equation. You can multiply both sides of this equation by x squared minus 4, right? To eliminate this guy. X squared minus 4. This is going to be 0, right? 0. And this is going to be, after you cancel these two, 3x. Dividing both sides by 3. This is just 0, right? This x equals 0. So what does it mean? It means that your x-intercept is going to be 0 comma 0, right? 0, comma 0, right? Yes, 0, comma 0. So y-intercept 0, comma 0, x-intercept 0, comma 0, right? Yeah, try to remember that, guys, because it's very common for this type of basic rational functions that we're going to study, that the y-intercept will be 0, comma 0, the x-intercept will be 0, comma 0 as well. All right, step four. Step 4 says find the vertical asymptotes, right? Vertical asymptotes. For that, we study a method, right? That method said after you simplify, remember, as you simplify, you simply set equal to 0 the denominator, right? This guy. So we go ahead and do that. Yeah, set equal to 0 that guy. So this yeah, right. X minus 2 times x minus 2 times x plus 2 must be equal to 0, right? Must be equal to 0. Great. From there, know how to see that x minus 2 equals 0, but also x plus 2 equals 0, right? And solving this equation, you will get that x is equal to 2 and that x is equal to -2, right? And turns out these are going to be precisely your vertical asymptotes, right? Vertical asymptotes, x equal 2 and x equal -2. Vertical asymptote in this case are these two guys, right? Very good. We got our vertical asymptote. Step 5, find your horizontal asymptotes. Horizontal asymptotes. Remember, for horizontal asymptotes, we have this method, right? We look at this structure of the rational function, degree here 1, degree here 2. It's bottom heavy, right? Bottom heavy. And for bottom heavy equations or rational functions, we said that the horizontal asymptote is just y equals 0, right? Y equals 0. Bottom heavy. The largest exponent is on the denominator, bottom heavy, then horizontal asymptote is just y equals 0, right? There we go. We got our horizontal asymptote. Finally, step 6 says graph or sketch the graph of this, right? We're going to do this together here. Yeah, I'm going to bring this XY coordinate system here. And again, guys, don't get obsessed getting a nice and neat graph. It's just a sketch what we need, okay? All right, so quickly, I would say, I would recommend you to set your vertical asymptote. Where is the vertical asymptote? Well, we said that the vertical asymptote is x equal to x equal -2, right? So x equal 2 is going to appear here, right? X equal 2. And x equal -2 will be here, right? So these are going to be the vertical asymptotes. Set them there. They will serve as an structure for your graph, okay? Now, we said that the horizontal asymptote y equals 0. Horizontal asymptote y equals 0. Set that also on your xy coordinate system, right? This is it here. So y equals 0 is your horizontal asymptote, and this guy's vertical asymptote x equal -2, vertical asymptote x equal 2, right? These are the asymptotes. They will serve as a structure for your graph. All right. Next, guys, what you have to do is try to go by parts, right? Because we know that this graph is going to come in 3 parts, broken, right? Let me start with this part, right? The one on the right. Then I will go to the one on the left, and then I will go to the middle, which is a little bit more complicated. But on the left, on this part, notice that the graph is it's asymptotic towards this vertical asymptote, right? Gets closer and closer to it, right? But also gets closer and closer to this horizontal asymptote. So one possible way for this could be this curve, but perhaps this curve, right? Perhaps, we don't know. We don't know. In order to determine which is the curve that you have to consider, use what mathematicians call test points. Test points. So test point. What is a test point? Well, a test point is going to be a point here on the right of 2. Let's say, for example, pick 3 for test point. Okay, x equal 3. And do this evaluation. F of 3. F of 3. F of 3. F of 3. Okay. The function is this, right? 3x over x squared minus 4. So let's evaluate this in our calculator. Let's see what the output value is going to be for 3 times x, which is 3, divided by 3 squared minus 4, right? Minus 4. I get 1.8, right? 1.8. Let's write it down. 1.8. 1.8. And this guy is telling me that this number 3 should be paired up with 1.8. So we're here, right? 1.8. So this guy probably. But what is this saying then? Well, it's saying that then the graph should be this piece, right? You follow, guys? Look, asymptotic there, asymptotic here, and going through this point, right? So you follow, guys? Getting closer and closer to this vertical line, getting closer and closer to this horizontal line. Not this, right? This, because of the test point, right? Yeah, great. Now, let's go to the left, right? Similarly, asymptotic here, so it could be this curve or perhaps this curve, right? We don't know. Take a test point, -3, for instance, right? Let's say -2 is there. -3 is here, right? And test, right? Test on your calculator where it goes. Is the function is 3 times -3 now divided by -3 square here, right? -4, right? -4. Great. -1.8, right? -1.8. So the result of using our test point, -3, f at -3, -1.8. So the evaluation of this guy, -3, comes down here, right? -1.8. So this is telling you that the curve that you have to consider is this one, right? Not this one, right? It has to go through the output values at this point. So then you decide, this should be this. Asymptotic here, right? Never touching. Asymptotic here. Let's make it nicer. So you choose that curve, right? So that's it. Yep. Left part. Now to go to the center, recall that we discovered that the x-intercept, the y-intercept was just this point, right? 0,0. So the graph has to go to this point. But now asymptotic here could be this way, or perhaps this way, or perhaps this way, right? Or maybe this way, right? The curve. We don't know. So to find out, use test points, right? Use test points. I'm gonna use as my test points, -1 and 1, right? So I'm gonna use 1 here and see where the output value goes, up or down, right? So for test point 1, test point 1 leads to f of 1 equal, if you put 1 in this function, look, 3 times 1, 3, 1 squared, 1 minus 4 minus 3 into 3 minus 1, right? So 1 is -1. You can get it in the calculator, right? So this one, guys, should be paired up with -1, should be here, right? Let's put a dot there. And similarly, if you use a test point -1 here, test point -1, test point -1, f evaluated at -1, the function evaluated at -1 will give you what? Look, -1 times 3, -3, -1 square 1 minus 3, -3, -3 into -3 is just 1, right? So this -1 is paired up with 1, ends up here. So look at these points, right? Look, I got this point, which is the xy intercept, and this point. So the only way for the curve to be asymptotic here and here going to these 3 points is this, right? Hope you guys will notice there is this, right? Asymptotic there, getting closer and closer there, then going through the origin because it's the intersection, and then going through this point, right? Like this. You follow, guys? So this is a good sketch for your graph, right? Look, this is here. They look like an elongated S, decreasing chair, right? This, right? All these 3 together. So now, by considering this, what should be the answer then here? Well, you look down here. The only one that is showing that to us is this one, right? See, you follow, guys? Decreasing share, this piece is this guy, right? Follow? The asymptotes are there, right? Excellent, excellent. Yeah, so this is when it comes to do graphing these rational functions. I hope you will be able to do this one at home, similar, try. But now let's talk about slant asymptotes, okay? Slant asymptotes. So what is a slant asymptote? Well, this is an asymptote that is neither vertical nor horizontal. It's an oblique asymptote. Oblique asymptote, okay? Yeah, so, and now you may say, Professor, how can I visualize this slant asymptote? Well, for example, if you do this in your graphing calculator, y equal, say, x squared minus 4 all over, say, x. You see here, this is a slant asymptote, oblique asymptote, right? For you to see it even better, I will show you this. You see it now? This is how a slant asymptote looks like. Look like this. It's not vertical. It's not horizontal, right? Neither vertical nor horizontal. It's oblique. Could look like this, or sometimes may look like this, right? It will depend. But in this case, for example, you can see, right? This. All right, and when these slant asymptotes appear? Well, they appear when you are dealing with a top-heavy rational function, right? Top-heavy. If this is top-heavy, right? If the degree of n of x is bigger than the degree of d of x, right? Top-heavy, and not only that, that difference of degrees for these two is just 1. So this guy is greater than this guy in degree by 1 unit, then it is there where the slant asymptote will appear, right? We will not have horizontal asymptote, but we will have a slant asymptote. Now, mathematicians discovered that this slant asymptote, the equation of this slant asymptote, can be found via division of polynomials, and precisely synthetic division, right? Which is something that we learned yesterday. So let me show you how. Find the slant asymptote of this rational function. Well, notice that this rational function is top heavy, right? Why? Because 2 greater than 1, right? Top heavy, and the difference between these two is 1, right? So then the idea is to perform synthetic division, right? So let me do it from scratch so you can see the synthetic division that I'm gonna do here. So we're gonna divide these two guys using synthetic division, okay? So if we recall what we did yesterday, right? If you do synthetic division, you're gonna get this, right? Remember, in the corner, we place this number with opposite sign, right? -1. Here we place 1, -1, 3, right? Bring it down 1, 1 times -1, -1, add -1 plus -1, -2, -2 times -1, 2, add. Finally, you get 5 here, right? 5. Separate the last number, that's the remainder, right? The remainder. And you can see that if you recover the quotient, this is the constant part of the quotient. This is the coefficient of x. So x minus 2 with remainder 5 should be the solution for this, right? But now this written in the other form. Remember this other form to write this, right? Let me just explain this from scratch so you can understand this part. Yeah, so this guy can be written as x minus 2 quotient plus, remember, the proper fraction. You put the remainder on the top and the divisor, which is x plus 1 on the bottom, right? Yeah, this is this division of two polynomials, right? But now notice that this part goes to 0 as x goes to infinity, right? For big values of x, this goes to 0. For big values of x. So it means that we can ignore this part. So we ignore this part, the one associated with the remainder, and we just keep this part. If you keep this part, this is going to tell you what the equation of the slant asymptote is, right? So you will say slant asymptote y equal this guy. So forget about the remainder, just pick up the quotient, y equal x minus 2 will be the equation of the slant asymptote, okay? Great. So now I want you to practice, guys, on this here quickly. It's pretty straightforward. You just do the synthetic division, and y equal the quotient should be the slant asymptote, okay? So let me show you this quickly with this one, and then I will ask you to do the next. Suppose they want you to figure out the equation of the slant asymptote for this top-heavy rational function. Well, you quickly go ahead and do this synthetic division. Notice this is minus 3. On the corner, you're going to put the opposite, 3. This guy has an invisible 1 there, right? 1, then 3, then minus 6, right? So 1 comes down as it is, 1. 1 times 3 is 3. 3 plus 3 is 6. 6 times 3, 18. Negative 6 plus 18 is just 12, right? Separate the last one, remember? So what is the result of this? 6 plus here 1x, which is written as x, with remainder 12, right? Remember 12. But remember, this can be written as x plus 6 plus 12 over the divisor, right? And this part, remember, we don't care about this part, right? This goes to 0 for big values of x, right? This 0. Ignore this, and then say slant asymptote will be just this. Y equal, the equation of your slant asymptote will be y equal this guy, x plus 6. You follow it? So just take the quotient, that will be the slant asymptote. Okay, can you try this one? Number 2. Let me give you the hint. Remember, it's top heavy, right? Yeah, here I should have written also top heavy to remember, right? Top heavy. Yeah, here top heavy again. So, and it's top heavy by 1 unit, so perfect for slant asymptote, right? So the hint is you have to do long division. This guy is minus 5 because we're gonna take the opposite, remember? Minus 5. And for the coefficients here of the dividend, 1, minus 4, and 9, right? Bring down this one and then multiply and continue, right? And then separate, ignore the remainder, right? It's just the quotient what we are after. Aha, I see. Aha. Lucero, great job. Good, good, good. Excellent, excellent. Very good, very good. You got it. Let's show how This is done. Yeah, 1 here, 1 times negative 5 here, negative 5 plus negative 4, negative 9 times negative 5, positive 45, right? And this sum is going to be 54, right? 54. But this, ignore it, right? Ignore it, because this goes to 0, right? Focus on this part. This is what will give you the answer, your equation, right? So I'm going to go straight here. Then slant asymptote will be what? Y equal, the equation of your slant asymptote will be this, right? Y equal, this is 1x minus 9, right? 1x minus 9. This is this part. Yeah, great. Excellent, guys. So this comes from there. Or this, ignore. Maybe I should write a little ignore. Because goes to 0 for big values of x. Right? That's the reason. So this is the answer. Excellent, excellent, excellent. This guy. All right. Now, to finish, let me show you. This is similar. You can do it at home, but this is different. And this you should be aware. They want you to graph this, right? Rational function, which happens to be top heavy, and therefore it will exhibit oblique or slant asymptote, right? Let me show you how you can do that. All right, first notice that if you simplify, this is already simplified, right? It's already simplified, so simplify. It's already simplified, right? Good. Now we go ahead with the vertical asymptotes. For vertical asymptote, I said that the denominator of the simplified version of this rational equation equal to 0, and this will be my vertical asymptote. Right? Vertical asymptote x equals 0. So there we have a vertical asymptote. So this should be my vertical asymptote, right? VA x equals 0, vertical asymptote. Now, this is top heavy, right? Top heavy. So, and not only that, this happens by 1 unit of difference, right, between these 2 degrees. So it means that we will have what is called a slant asymptote. For that, we, in theory, should apply synthetic division, right? But notice, guys, that this quotient is really very simple, very simple. I don't need synthetic division. I can just divide x into this, right? So x into x squared will be just x plus 4 over x, right? But we said that this part, right, the one associated with the remainder, right? This guy for big values of x goes to 0, right? 0 for big values of x on the left or on the right, right? Yeah, so forget about this, right? And just keep this. So then your slant asymptote will be this, y equal x, right? This is the quotient, y equal x, right? Yeah, great. And where is the graph of y equal x? Isn't it this diagonal line, right? Y equal x is this, right? Y equal x, diagonal line, right? Now, the issue is, right, is it this curve here, asymptotic to the blue vertical line, asymptotic to this slant asymptote, right? Is this curve or maybe this curve, right? I don't know. And similarly here on the left side, right? Is it this curve or is it this curve, right? Well, for that, use test points, right? Test points to make sure which curve you're going to take. The test points will tell you. For example, I can use test point 1, right? 1, test point 1, and evaluate my function at 1 and see what I get, right? What is this evaluated at 1? 1 squared is 1, 1 plus 4 is 5, 5 divided by 1, 5, right? 5. It's giving me a positive value for 1. The output value should be 5. So the graph should go to this point, right? So this is telling me that the curve that I have to consider must be this guy, right? This curve. Sorry. This one on the top, right? This curve should be the one. You follow, guys? It's gonna contain this point, right? And this way. Yeah. Cannot be this curve because it will miss the output value of my test point 1, right? Test point was 1. For the left side, similarly, take a test point, for example, test point on the left of 0 now, test point -1, let's say. Figure out using your calculator what is the output value associated with the input value -1. Look, this is going to be -1 squared. Guys, you can do it in the calculator in case you feel like the numbers are not friendly, right? -1 is squared. That's going to be just a 1 plus 4. And all this divided by -1, right? What is that? Is -5 now. -5, negative number, right? -5. So this -1 that here should be paired up with -5 down here, right? So the point now is down there. So which means that the curve that corresponds to the left side of this should go like this, right? Asymptotic here also, right? Asymptotic there. And this should be a good sketch, right? They just want to sketch. Later on in calculus, they will show you where to identify precisely where is the lowest point, where is the highest point, right? Right now, this should be enough to identify your answer, right? So by looking at this, guys, what do you think should be the answer then? Anybody? A, B, C, or D? By looking at this, what should be the answer? You can type it on the chat. Aha. Yeah, all you gotta do is you gotta just be careful with these asymptotes, right? Aha, very good, Lucero. Excellent, excellent. Jing also, right? Very good, Jing, Lucero. Yeah, it's gonna be this guy, right? Look, here is this piece, right? And here is this piece, right? But be careful, guys. Sometimes, because of the test points, right? In this case, the test point was -5. That's the reason why we took this piece, right? And this one was 5. That's the reason we took this piece. But if let's say you evaluate that one and you get negative number here, then it will be this piece, right? It will look like this, right? Like this guy. So be careful there. So in some examples, you may end up with this shape or sometimes this shape, right? Yeah, great. So be careful there. Okay, guys, that's enough for today. Let's